All right, today we're going to learn about the power rule, which is going to ultimately make our lives a lot easier now that we won't have to use the limit definition of a derivative. So first we're going to fill in this chart. We're going to deal with the function x squared plus 1. We're going from values from x equals -3 on up to 3. And we're going to find the function value, the slope, and then we're going to graph it. So first thing we're going to do, we're going to let the calculator help us out with this. So we're going to go to y equals, and we're going to put in x squared plus 1. Okay, if I go to so a standard window is fine. Okay, there's our parabola. No surprises there. What we're going to do is we're going to find the function value and the slope all in the same step. So if you go to second calc, we're going to calculate down here dy dx. That is the notation for the derivative. So this is going to give us the derivative or the slope at a specific location. So I'm going to do that, and then I'm going to type in -3. And what you see here is x equals -3, y equals 10, and dy dx equals -6. So that's what we're going to put in our chart. So this is 10, this is -6. For the graph of the tangent line, I'm not going to worry about this part too much. I'm just going to say, here's my parabola, and at 1, 2, 3, my tangent line looks like that. Okay, so a slope of -6 seems to make sense. And then we're going to repeat this for all the others in the table. So I'm going to second calc the derivative at -2. I get an x value of -2, a y value of 5, and a derivative or slope value of -4. And for my graph, parabola, 1, 2, tangent line. Okay, so we're going to fill out the rest of the table like that. So here's the whole table filled out. So hopefully you went through and did this, or you can copy it down. What we're interested in right now is the relationship between the x values and the particular slopes. So we're going to use the table values from the front side to fill this in. So starting at -3, we're down at -6, -2 is at -4, -1's at -2, 0 had a 0 slope, then we're at +2, +4, and +6. Well, what type of graph is this? This would be a line. And we can easily come up with this equation because it's a line. Has a slope of 2, y-intercept of 0. So the equation of that line, which represents the slopes on the parabola, is y equals 2x. All right, we're going to graph more functions. Basically, we're going to increase the power and see what happens with this and the derivative. So back to our calculator. Okay, so now we're going to change this to a 3. In y2, I'm going to graph the derivative. So we're going to go to alpha f2. 3 is the numerical derivative. So we're going to do d dx alpha f4 y1 x equals x. And if you don't have a TI-84 and you need help figuring out how to do this on your calculator, we can work that out. So now when I graph it, we're going to see the cubic function, and then we're going to see its derivative. Okay, so the blue one is the cubic function, and f prime was the red one is the derivative. So describe the graph. The derivative is a parabola. Okay, and you can go ahead and copy this picture into your notes. All right, so next up is going to be a quartic. We'll graph that. And then its derivative. Okay, so that looks like a cubic function. Okay, let's see. So that would be something y equals something cubed, right? So if I trace on the derivative, and I trace to, say, 1. Okay, we get a value of 4. On a regular cubic, if I put in 1, we'd get 1. So this is actually going to be 4x cubed. So let me go back to this one a little bit. So we said it was a parabola, so it's going to be y equals something squared. And if I trace on the derivative, if I trace to 1, it's up at 3. So this would be 3x squared according to the calculator. And we'll do this one more time with a 5th power. So when we graph this, okay, 5th power levels off there. And then its derivative, okay, kind of looks like a parabola, but when it levels off here in the middle, that means it's got a higher degree than just a regular parabola. So this would be a quartic function. So something y equals something to the 4th power, and then again I'm going to trace at 1, and we get 5 there. So this would be 5x to the 4th. So we're looking at the relationship between the function and the function, the derivative. There's the function, there's the derivative, there's the function, there's the derivative. So x squared went to 2x. X cubed plus 1 is 3x squared. X to the 4th is 4x cubed. X to the 5th plus 1 is 5x to the 4th. So hopefully you see a pattern here where the power gets brought down out front, and then the power itself drops by 1. So we're going to use that pattern to fill out this table. So if our function is x, our derivative is going to be 2x. Derivative of x cubed is 3x squared. Derivative of x to the 4th is going to be 4x cubed. 5 is going to be 5x to the 4th. 6 is going to be 6x to the 5th. X. This power would be 1, so we'd bring the 1 down, and then we'd subtract, which would be to the 0th power. Or if you just think about the line y equals x, its slope is always 1. A constant, thinking about it graphically, it would be a horizontal line, so the derivative of any constant is 0. X to the 100 is going to be 100, x to the 99. X to the n then, so this is our general rule, is going to be n x to the n minus 1. Okay, so now let's do this not just with the calculator, but actually by hand. So remember, the definition of a derivative is going to be the limit as h goes to 0 of f of x plus h minus f of x over h. So we're going to use that to verify algebraically what we seemed to find graphically. So for this first one, we're going to look at the limit as h goes to 0 of f of x plus h. Well, f of x plus h is going to be c. F of x is c over h. So we get the limit as h goes to 0 of 0 over h, which is just going to be 0. For x, the limit as h goes to 0 of f of x plus h. So that's just going to be x plus h minus f of x, which is x, over h. So x minus x is 0, so we have h over h, which is just 1. And the limit as h goes to 0 of 1 is 1. Okay, let's do a squared. So the limit as h goes to 0 of f of x plus h, so h plus x plus h squared minus f of x over h. We're going to FOIL that out. Squared all over h. So the x squared minus x squared is going to go away. And then the things that are left have an h in them. So this will be reduced by h, so that will be 2x. And then this will be reduced by h. So we have the limit as h goes to 0 of 2x plus h, which is 2x. So we saw that. Let's do a cubic function, and then we'll kind of start to see where this rule is coming from. Okay, so how do you deal with a cubic function? You use the binomial theorem that you guys all learned from the comfort of your home last year. So we're going to expand this out. We use the third row of Pascal's triangle, which is going to be 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So those are going to be our coefficients. And then remember, the first thing goes down by power and the second thing goes up in power. So this is going to be the limit as h goes to 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. Well, again, and this is going to happen every single time, that first thing is going to get taken out. Everything that's left is going to have an h. So this gets divided by h, which leaves me with 3x squared. This, and then this, h squared. The only thing that no longer has an h now is that 3x squared. So this is the limit, not the limit. When I evaluate this limit, all that's left standing is that 3x squared. So the way this is working really is coming from the binomial theorem, that in the binomial expansion, this and this are always going to cancel, and what's going to take over is this second term. The second term is always going to have the power in front of it, and then the x one less. And I'll share a video of the proof more generically than just this, if you are interested in watching this. But we can now say that the derivative of x to the n and we're going to use that symbol prime, that the derivative is nx to the n minus 1. So you're going to want to make a note card for that. Okay, what about if we have a coefficient out front? Well, that's just going to get multiplied in. So the derivative of that is just going to be the constant times the derivative. So if I do this derivative, we're going to bring down the power, so it's going to be 5 times 30x to the 4th, which is going to be 150 x to the 4th. For a sum, the derivative of the sum is just going to be the sum of the derivatives. So here, the derivative of this entire polynomial is just the sum of the derivative of this plus this plus this. So f prime of x, we're going to multiply that down. So this is going to be 8x when I subtract the 2 minus 1. The derivative of 5x is just going to be 5, and the derivative of any constant is 0. So the power rule is a pretty neat thing. So how would we handle something like this? Well, first we're going to have to expand it, and then we'll take the derivative. So again, I'm going to use the binomial theorem here. So this is going to be 3x cubed plus 3 times 3x squared times a negative 2 plus a 3 times 3x times negative 2 squared plus a negative 2 cubed. So remember, we take the row of Pascal's triangle, so 1, 3, 3, 1. The first thing starts at the highest power and decreases by 1, and then the second thing starts at 0 and increases. So we'll simplify this. So 3 cubed is 27x cubed. Here, we're going to have, this will be minus, because it's going to be a negative 2 times a 9 times a 3, which is going to give me 54x squared. Here I'm going to have a 4 times 3 times 3, which gives me 36. And then negative 2 cubed is going to be a negative 8. So then I'm going to take the derivative. So this 3x minus 2 cubed is equal to this. So the derivative is going to equal the derivative of this. So 3 times 27 is going to be 81x squared. 2 times 54 is 108x plus 36 plus 0. All right, so what about things that aren't just whole numbers? Can we still apply the power rule? So I'm going to do this using the definition of a derivative. So the limit as h goes to 0 of f of x plus h minus f of x over h for this function is going to be the square root of x plus h minus the square root of x over h. Well, now what do we do? So we do some fancy algebra here. I'm going to multiply by the conjugate of this, because that's going to get rid of the square roots. So I'm going to multiply by x plus h plus the square root of x okay. So when we FOIL on the top there, this times this is just x plus h. This times this would be positive the same thing that I get here, which is negative. So those middle terms go away. That's the point of the conjugate. Then we're going to have a negative x square root of x times a positive square root of x, which is just going to be a negative x. All over on the bottom here, plus the square root of x. Okay, well in the top, the x minus x goes away. So we're left with h over h times the square root of x plus h plus the square root of x. These h's cancel. Go up over here. So the h is reduced. I'm left with 1 over the square root of x plus h plus the square root of x. And now I can go ahead and evaluate the limit. So I'm going to plug in a 0 for h. So I'm going to have the square root of x plus the square root of x, which is 1 over 2 square root of x. So from the definition of the limit, we get this. What about the power rule? Well, the square root of x is equal to x to the 1/2, which is a power. So let's use the power rule. So the power rule says we're going to multiply down the power, so that's going to be 1/2. And I'm going to subtract 1 from the power. So 1/2 minus 1 is a negative 1/2. Well, that doesn't look the same as that, but let's think about this. This would be the same as 1/2 times 1 over x to the 1/2, since it's negative, and that's just the square root. So this is equal to 1 over 2 root x. So on a note card, the derivative of the square root of x is 1 over 2 root x. For now, if you forget, you can always just apply the power rule, but that is one that you'll want to know eventually for square root. All right, next up, 1 over x. So I'm going to use the definition of a derivative again. Using 1 over x. So we're going to have 1 over x plus h minus 1 over x all over h. And we're going to have to do some work here. So I'm going to get a common denominator up here. So I'm going to multiply this one by x over x. So I'm going to have x times x plus h minus, here I'm going to multiply by x plus h over x plus h. Okay, if I combine this now, the top I'm going to have x minus an h. So that's going to give me negative for x plus h times a 1 over h. Okay, so dividing by h is the same as multiplying by that reciprocal. So the h here and the h here cancel. So we're left with a negative 1 over x plus h. So as we go to 0, as h goes to 0, we're going to have negative 1 over x times x, did the limit, which is negative 1 over x squared. All right, the power rule. 1 over x is equal to x to the negative 1 power. So if I take the derivative, I multiply the power down, and I subtract 1. So we get negative 1 times x to the negative 1. Well, that equals negative 1 over x squared. So there's another card. The derivative of that is negative 1 over x squared. Just quickly, the difference between a vertical tangent and a cusp. So this one here, the graph is going to look like this, which has a vertical tangent. This one, and you can graph these on your calculator, is going to look like this, which means that there is no derivative here and there is no derivative here. So let's look at how that plays out algebraically. So if I take the derivative of f of x, we're going to have 1/3 x to the negative 2/3, because I'm going to subtract 1. Well, that's going to be the same as 1 over 3x to the 2/3. So if I plug in 0, that derivative is undefined. Same for g of x. We get that negative exponent again, so this would be 2 over 3x to the 1/3, which would be undefined at 0. Feel free to graph them. They're a little bit interesting, and you can look at the differences. But the big thing here is that even algebraically, there is no derivative at 0. Okay, notation. You've seen a lot of different notation, and right now it seems new, but it will become more common. You'll use certain ones. So this notation, dy dx, we're going to use a lot. So it's representing slope. It's the instantaneous slope. So the difference in y over the difference in x. Sometimes you're just going to see it as dx there. Bernoulli, not one that we're really going to use. So that's there. Lagrange we've used a lot, so the f prime notation comes from him. And then Newton, who's pretty involved in calculus, uses a dot, but we're really going to use that and that notation. Okay, if f of x is x, then f prime of 5 is what? Well, f prime of x is just 1, and f prime of 1 is just 1. And then for this one, we're looking at the limit definition. So if our function is e to the x, so we're looking at looking at the definition. So this is the one that matches. This is f of a plus h. This is f of a, which in this case is e. That's going to be our correct choice there.